Good morning, everybody, and welcome to our SAIMM webinar series. Welcome to everybody who's on the line this morning. We're going to today hear from Arrie van Niekerk. Arrie has been working in this area of theory of constraints in mining for a long time and over many operations and continents. So the webinar will indicate why it's possible for a company with its installed infrastructure, the same people and the same equipment to produce typically 10 to 40% more in terms of output. The results are achieved within a short time frame. And these projects were implemented in more than 90 operations on 5 different continents over the past 20 years. The theory of constraints optimized flow approach requires a change in the way that we think, the way that we plan, the way we measure, and ultimately how we behave in our operations. It is founded on the theory of constraints solution for production flow, project execution, logistics and financial decision-making, and includes specific leadership and behavior components. The focus is on the bottleneck, buffer management, and people alignment, which requires a holistic leadership and management approach in order to deliver results. So with that, I'd like to hand over to Arrie, if I may, please. Arrie, are you ready?
Yes, Alistair, thank you very much, and thank you for the introduction. Thank you once again, Alistair and Camilla, for organizing it. It's a privilege for me to do this with South African Institute of Mining and Metallurgy. We've been working with the theory of constraints for the past 20 years, and as you said in the introduction, we saw some phenomenal results. Now, what I want to do today is to give you an overview of the theory of constraints as we apply it in mining. In the time frame, I want to cover the TOC as we apply it in production. I will touch on project management because we use project management in development, especially in underground mining. Also, the replenishment approach for online underground stores, and also for mines in remote places. And then I'll just want to cover briefly on the financial measurements. And then I want to talk a little bit about the leadership and also the strategic application of the theory of constraints. What I'm going to do is to share with you in all these aspects of theory of constraints, the essence or the snippets that I believe is really taking this approach into a new era. We've seen phenomenal results, and all of this was done by the people on site themselves. They had to change the way they do things, and in many cases the results were just phenomenal. So I'm going to also say a few things today that's quite controversial. I want you to be comfortable with it. I'm going to make some statements that for some of you, it might make your hair stand up. Just bear with me. I'm also going to take some quotes from Dr. Eli Goldrad's books and some of the work that he did. And this is just to show how radically different theory of constraints is from the normal way we do things. Now, I don't know whether you know it, but the way we operate, especially in the mining industry, in terms of efficiency and our organization structures, these concepts are more than 100 years old, and they've served us very well for very long. In the process, we became smart, we became faster, we became leaner, we became very efficient. The whole world started operating with very low stock levels and very high reliability and availability of people. And then recently with COVID, all of that changed. It will probably return back to normal. But maybe the question is there another way? that we can do things that will help us to perform significantly better. And I want to share with you the theory of constraints approach to doing this. I'm going to cover conceptually what is theory of constraints and a little bit of what it's not. Then I will talk a little bit about mining operations and then working on project nature, the supply chain, the daily ops room, and or the war room. We took the concept from the military for very good reason, the new leadership requirements, and then it's the strategic application. Now you can sense from this, I want to cover a very wide subject in a very short period of time. So what is the theory of constraints? It's a business approach and business management approach as developed by Dr. Eddie Goldratt in the late 1980s. It was popularized by his book, The Goal. And I personally believe a book that's a worthwhile read is The Race. It approaches the same subject, but from a different angle. It's a holistic business approach that focuses on the flow and constraints. It buffers for variation and it builds system resilience. It's a little bit different from the normal way we do it. And typically we see a net present value improvement of 20% or more. And it's all about creating reliable and predictable flow. I want to share two slides with you just to whet your appetite for the rest of the conversation. This was published by Ernst & Young a bit more than 2 years ago. And on the graph, you see the red graph, that's labor productivity in the mining industry, while the gray line is labor productivity in all sectors. This was in Australia. The worrying part is this component here is the red curve that showed for quite some time the labor productivity in mining went up. But then around about 2000, 2003, I'll show you another graph that has got a slightly different time frame. The mining productivity all over the world, in Australia, started dropping. This is the Mine Lens Productivity Index by McKinsey & Company. And this is a similar graph with a baseline of 100 in 2004. You can see that the productivity dropped by 40% by 2010. And maybe the real question that I want to just stimulate you and just put this in the back of your mind. What caused this? And I'm going to hint towards that, and I hope you'll enjoy that link. Now, I have developed an approach or a demonstration over the years, and it just happened by chance. If you can see on the video, it's just a normal bottle full of water and a bucket. And I'm going to use 3 different scenarios in showing how the bottle will perform, how the bottleneck will perform in this bottle, and what the bottleneck will do in this demonstration. So it's just a normal glass bottle. It's a 1.5 liter wine bottle. And I fill it with water, and then I overturn it. And bottle 1 is the left one on the left. I just call it bottle 1, bottle 2, and bottle 3. And by the way, this is also available on YouTube if you want to go and have a look at the more detailed version of it. And in the first bottle, I'm just going to overturn the bottle and let it flow. And then I'd like you to observe what happens to the flow in the bottleneck itself, and then secondly, inside the bottle. The second bottle is exactly the same system, but with slightly different energy. I'm going to overturn the bottle and twirl it. And then you'll see how the dynamic changes and how the end result changes. And then the third bottle, I'm going to insert a straw. And the straw, the purpose of the straw is to channel the air. And then you'll see the real impact of that bottle. So I'm going to stop the slideshow and just move to a video clip that will demonstrate this. And just help me if you can see it. Ah, there it is. You should be seeing it now. So on your screen, there should be just a black screen, and you can see it's a video that's going to show. So please observe, ladies and gentlemen, what happens in the bottleneck, and secondly, what happens inside. the bottle, and then you can see on the side how long it actually takes. There it runs. This is what happens inside the bottle. Lots of turmoil, lots of movement. And then in the bottle, you can see it's erratic, it's unstable, it's unpredictable flow. And that dynamic simply doesn't work. And if you have the stopwatch on the side, you can see it takes 19 seconds for that bottle to empty. So this is the world where I talk about bottle one, is the world of unstable flow. It's unreliable, it's unpredictable, lots of turmoil, lots of silos. And let me put some human words to it. Lots of infighting, backstabbing, firefighting, and the production flow simply doesn't work. This is bottle one. Bottle two is it's the same bottle, but slightly different energy. Please have a look at how this one works. And watch the time on the side. So I twirl the bottle to create the vortex. And then the dynamic changes completely. Look at the flow. And then the beauty is the time went from 19 seconds to 12 seconds. In the first bottle, what happened in the bottleneck, there was a conflict between the water and the air. Because at the moment I overturned the water, the water started to flow, created a vacuum inside. And then the water flowed and the vacuum kind of held the water back. And the only way to relieve it was to suck in a bubble of air. That was what was happening in the first bottle. The second bottle, I created the vortex so that the air could go in and the water can come out simultaneously. And that made a big difference on the flow. It's a stable, reliable flow. And inside the bottle, the dynamic was completely different. This time, all the molecules were working together. Let's call it shared vision, shared objectives, and good alignment of everything in the system. This is bottle two. Now, bottle three is where I insert the straw. And we will start the timer because I'm going to blow in the straw just to kickstart the process. And then you'll see what happens. But watch the time. Watch the time. Almost magic, isn't it? Let me show you the slightly slower version of it. Watch the flow, despite the fact that there's a straw in the bottle. Look inside the bottle. I just want to go back to the PowerPoint. Sorry for the delay. Can you see my screen? Can you see the PowerPoint slide?
Yes, we can.
Yes.
Thank you, Arrie.
Thank you very much. So, ladies and gentlemen, we've got bottle one, bottle two, and bottle three. The last bottle, I mean, the time was so fast. It's almost, you have to, after you held your breath, it's over. I call it the world of superflow in the spirit of calmness. Superflow excellence in the spirit of calmness. That's bottle three. But ladies and gentlemen, here's the key insight. In all three cases, the bottleneck was the same. I did not make any change to the bottleneck itself. But what I did is I changed the rate of flow through the bottleneck. And I believe this is the key insight of theory of constraints, what it's all about. It's not about debottlenecking. Many people out there believe theory of constraints is about debottlenecking. It's not about debottlenecking. It's about making the bottleneck work significantly better. In other words, increasing the flow through the bottleneck. And that's what I want to do. Oh, and this is looking at many implementations. This is typically where we start. This is bottle one. And then we stabilize the flow at slightly higher than budget. And that gives us, that's after 10 to 15% improvement. That's bottle two. And then bottle three is actually where we want to be, where we've got phenomenal leadership and focus and everybody working together. And these are the kinds of results we've seen over the last 20 years. And these are just the numbers. We can come back to these slides, but you can see deep level gold, medium level platinum, open cast iron ore, diamond, and copper, phenomenal results all over the world. And now I want to share with you how we actually do it. Now I want to explain theory of constraints in the world of a complex environment, because our mining operations are fairly complex. And in the center of this picture, you can see that that's where the primary production flow happens. And we all know that the primary production flow is not all what it's about. You need maintenance, you need spare parts, you need consumables, you need training, you need HR, you need safety, all of those things. And this makes our world a very complex world. But I want to explain the process just with a center portion of 6 resources in series. In other words, a serial production chain. And then at the appropriate time, I'll make the link back to this picture into the complexity again. So let me start with that picture. And this is what it looks like. And the numbers that you see in those bubbles is the average capacity in tons per hour. In other words, the purple resource can do on average 15 tons an hour. The green one can do on average 16 tons an hour. And then the turquoise one, 14 and 10, 13 and 12. And I've structured this picture in such a way that you can clearly see, and I've even colored it the right color, that there's a bottleneck in this system. And this system is unbalanced. The capacity is not balanced properly. And most people are very uncomfortable with this design to a degree that many years ago somebody told me. He said the person who designed this chain must go and get his money back from university because it was a waste of money. This is not what we want. This is not typically what we see. But what we want, when we look at our budgets, how we do our budgets, we start at how much we want to produce, and then we work our way backwards into processing. We work our way backwards into load and haul, drill and blast, and overburden stripping or development, whatever. But if you carefully inspect and look at the way we manage our production chains and how we budget it completely different from the previous design. We budget it as a balanced capacity chain where all the resources must be utilized fully, all the resources must be used efficiently, and we manage for the lowest possible cost of the system. And this is what I refer to as a balanced capacity chain, where everything is equally important. And the belief is if every resource just do their job, the system will be fine. But now I want to show you what will happen based on 2 scientific facts, variation and interdependence. And you will see that the interdependence is the real killer. Look at these 2 resources, and I'm interested in what will be the result of these 2 resources in series. And this is how the purple resource fluctuate, and this is how the green resource fluctuate. So what's coming out this end? In the beginning, everything is fine. Just more than 10 will report here. But then something goes wrong. Well, just normal variation on the purple one. The purple one drops to 8. It sends only 8 to the green resource. And of course, the green resource can process the 8 and pass it out. A little while later, the green resource drops to 4. It blocks the purple resource from doing more than 4. And only 4 reports out at this end. So what's coming out this end of this chain is the superimposed graph of the 2 variations. And I'll color it in with red so that you can see it. And immediately you can see this chain is producing significantly less than 10. Well, maybe not significantly, but definitely less than 10. But you remember we started off with 6. So what will happen in this chain? This is the 2 resources that I showed before. And then I add the turquoise one and then the red one. And you can see the red one struggles a little bit in the beginning. And then it catches up, and then it struggles and it catches up. But it averages just below 10 maybe. And then the purple one, and then the yellow one, and then the blue one. And suddenly you see, if I give you a sneak peek on how much this chain is producing, it's producing only 5. And you can sense that I over-exaggerated for effect. But just bear with me. This chain will produce only 5. What will the culture be? But I need to ask you a very important question at this point in time. Which color do you think is the bottleneck? Which color do you think is the bottleneck? And when I'm standing in front of a group of people, now I cannot do it because I cannot see you. some people will vote for yellow, because this is quite obvious. The yellow is a big problem in this portion of portion of time. Then it's a problem again. The purple one also surfaces, and then if you carefully look, the red one. So it could either be could be any one of them, but eventually people will tell me, but it's all of them. Or more correctly, is the design of the system. What will the culture be in this organization? Because we're manned and equipped for 10, we're producing only 5, our costs are through the roof, we have to constantly explain to the shareholders what we are doing with their money. System is not producing. Where do we focus in the next 24 hours? So this becomes the world of firefighting, of blame shifting, of finger pointing, and it doesn't perform. And this, ladies and gentlemen, is bottle 1. The world of balance capacity, because the balance capacity chain where we try to optimize everything will never ever deliver. And this is the real challenge. I think I've showed you here that the 6 resources in the center will produce only 5. How much will this system produce? Let's give it the benefit of the doubt and say this balance capacity system will produce maybe 4. How long will the shareholders man and equip you for 10 and you produce only 4? What will eventually happen? They will cut it. They'll cut everything to 8. Then the system will produce 3.2. Then we cut it to 6 and the system will produce 2.4. Then we cut it to 5 and the system will produce 2, because the behavior in the system won't be different. And then somebody will raise their hand and say, whoa, 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 whoa. This is not a profitable organization. Close it or sell it. And here's the real insight. The closer you are to a balanced capacity chain, the closer you are to bankruptcy. This is a quote from Dr. Eli Goldratt. And here's the reason. The combined effect of variation and interdependence destroys the flow. And the real dilemma is the interdependence, because in the interdependent chain, the weakest link determines the output of the chain. And that's why the systems will not deliver. This, ladies and gentlemen, is the signature characteristic of a balanced capacity environment. And I hope this doesn't look familiar from your environment. There's the budget, is the green line. We're not making budget. We're struggling because we always fall short. And there's huge variation from day to day. So this is your daily output graph. It's a very clear indication that you've got a balanced capacity environment. And then I get very excited because there's huge potential for improvement. This is a picture of such a balanced capacity chain. And forgive me for this. This is just a coffee station at a conference setting. And on the picture, you can see there's the urn, there are the cups, and the coffee and tea and the sugar and the milk at the back. Now imagine what will happen during the break, during the conference break, and everybody rush to the coffee station. What's going to happen? A person is going to grab the cup, then he puts some coffee and sugar in it. Then he moves to the urn to get the hot water. And then he's got to fight his way back between all the other people to get to the milk. You can see one person will occupy the station. There will be no flow, and there will be the normal queue that we always see. And the real question is there a different way? Is there another way that we can arrange this table for flow, and you'll get a completely different result? But in this picture, the flow is absent. And now I want to show you bottle 2. And here's the process. Here's the theory of constraints process. Step number 1, identify the constraint. Step number 2, decide how to exploit the constraint. Step number 3, subordinate everything else to the previous decisions. And I'm going to elaborate on step 1, 2, and 3 just now. But then ultimately, if the 10 is not enough, you buy more capacity, you make the 10 a 12 or a 15 or a 16. And then obviously there will be a new constraint. This is the part where we debottleneck the system. But in our normal approach, by that time, we'll be producing 30 to 40% more. And this becomes a continuous process of improvement. So let me start this process. In the original picture that I showed you, this is very clear. There's the bottleneck. It's the 10. It's the resource with the least capacity in the system. So it's easy to identify the bottleneck. And then the realization that the bottleneck determines the revenue output of the system as a whole. So if the 10 stands for a day, the whole system effectively stands, because the system can only produce as much as the 10. And if the 10 is running at only 80% of its capacity, the system is producing only 8. Here's the insight. 1 hour lost on the bottleneck is 1 hour lost for the total system forever. This is not monopoly or funny money. This is real money. Think of a mining operation where the whole mine stands because the vertical shaft was out of order. It wasn't working. You never recover that. You never recover that because the bottleneck has no recovery capacity. So in the presence of a bottleneck, all the rules change. So this is step 1, identify the bottleneck. In the balanced capacity chain, it's extremely difficult to identify the bottleneck. But let me just park that for now. Step number 2 is exploit the bottleneck. Look at the bottleneck itself. Zoom in on the bottleneck and ask yourself, what do I have to do to maximize the bottleneck's output? Running time, it has to run 24 hours, 7 days a week. I've already spoken about the implication of standing time. Under those conditions, what should the maintenance philosophy be? Where do you want the spare parts to be for the bottleneck? Not somewhere in Johannesburg or on some remote site. You want the spare parts of the bottleneck on site and enough of it. Full preventive maintenance is a prerequisite for the bottleneck. If on a Monday morning, the operator of the bottleneck doesn't turn up for work, you must have a spare operator that can step in immediately and run it at 10, not at 5. Because if it runs it at 5, you lose half the cost of the business. Quality control. You don't want the bottleneck to process scrap. You want the bottleneck to process good stuff, so you do your quality control in front of the bottleneck. The product value. You can, if you push waste through the bottleneck and you push low grade and high grade, this is the very interesting thing. On an hourly basis, you can calculate how much money we're making by just looking at the value going through the bottleneck. You don't have to wait for month end. You can do this almost on an hourly basis. What should the bottleneck be working on and what should it not be working on? These are the key questions we have to ask. So this is step 2. Step 3 is probably more important than anything. I must make sure that the bottleneck will never be out of work. And for that, I'll put a buffer of work in front of it and offloading space behind it. A buffer of work I want full. That's why it's green when it's full. And the offloading space, it's green when it's empty. So there's a free flow through the bottleneck. So the bottleneck will always have work and it will never be blocked by any downstream activity. Under these conditions, the bottleneck will perform it at its maximum rate. And thinking of what we've just done. But of course, there's another part of the system that needs to supply this bottleneck. And let's assume that the bottleneck is full, but something goes wrong with the turquoise resource, and the turquoise resource books off for a breakdown. The immediate impact on the bottleneck is nothing. The bottleneck draws from the buffer. But as it draws from the buffer and there's no inflow into the buffer drops to yellow, and then the urgency to repair this goes up. And then eventually it goes into red, and then the urgency is really up there. And let's assume just before it's empty, I get this chain going, this upstream chain. What should they be doing? They must rebuild the buffer while they are keeping the bottleneck going. In other words, everything upstream must have more capacity than the bottleneck, or else the bottleneck will run empty and the business will be losing millions. So everything upstream must have what I call protective capacity. The same logic applies for the downstream. Now, ladies and gentlemen, this is a completely new design. It's not the balanced capacity of 10, 10, 10, 10, 10. It's a capacity where the bottleneck is the 10. Everything else must have at least 20% more capacity. And I'm just jumping the 20% on you, but you can figure it out. That's more or less what you need. Because if you've got 20% more capacity, you can rebuild that buffer in 5 days. And that's more, sometimes it's not enough, but that's the minimum you kind of need. I want to show you the effect on the previous graph. Put the buffers in place, and now the kind of miracle happens. The output of that chain is now only determined by the red resource. And there's the red curve. And let me color it in so that you can see. By just putting in the right buffers and managing them properly with enough capacity to protect, to build the buffers, that chain will produce 15 to 30% more. There's no rocket science here. It's just applying the principles of flow. So here's the new design. You must know where your bottleneck is. There must be a buffer of work in front, space buffer behind. Everything else must have spare capacity. So this is the difference that we're talking about. The top one is bottle 1 and the next one is bottle 2. And this is the significant shift that we have in production flow chains. Here's Dr. Eli Goldrath's statement. If you want to make money, most of your resources must be idle from time to time. And in any serial production chain, you can optimize only one link, not two. So you should never have two interactive bottlenecks. It will kill the flow. Do you want to make money or do you want to show off efficiencies? And this is the bottle 2 plus design. You can see the bottleneck is very well protected in terms of flow, maintenance, spare parts, operators, and downstream. So this system is set up to serve the bottleneck and make the bottleneck work. And this is the ultimate flow system where the bottleneck will get to its maximum utilization and capacity output. What about this statement? Efficiencies, costs, utilization, availability. These measurements tell you nothing about the overall performance of the business. On the bottleneck, it's extremely important, but not on non-bottlenecks. So a question that comes up quite often is, where should the bottleneck be? And here's my quick answer. We can have a long debate about this. Should be the most capital-intensive resource. Not something that's relatively easy to replace, not a truck or a shovel or a drill, and not a loadout station or a leach tank. So during the, but also we need to, I need to qualify this. During the life of mine, the bottleneck will shift from when you start up the mine and when you end off the mine, and in between, the bottleneck will definitely move. And we have to really think very carefully on where do we want that, at what stage, and how do we change the management approach during those phases. This is a picture, and I've normalized it to a million tons. It's a ramp-up plan. You see the blue curve was the ramp-up plan, taking out up to 760,000 tons a month of ore. And we implemented, they started slipping over here. You see that was stabilizing at this rate. We introduced the production flow engagement there. We initiated the war room, and you could see then the production started lifting. We also implemented rapid results. And ultimately, this operation went to 1 million tons, and at a design capacity of 760, which was a remarkable feat for this team who did this. And they continued doing this level of this kind of performance for years to come. It was an amazing story. So here's the difference. In the world of efficiency management, it's a balanced capacity approach. We want to optimize every link in the system. It's all about local optima. And the TOC flow management is to maximize the flow of the whole. We focus and manage on the bottleneck. We buffer for variation. By the way, in theory of constraints, variation is not the enemy. We embrace it. And then we provide protective capacity. This is the new flow model. So how do we apply these same principles in the world of projects? This is just a picture of a project. But I wanted to just share two components with it, on it. This is the probability of task duration, and you understand this. There's a certain minimum time in which you could do the task if everything is perfect. And then there's a kind of a normal 50% probability of doing it in 5 days, but also 80% probability of doing it in 10 days. Most of our project plans work on the 80% probability, so there's safety in there. The way we use this in theory of constraints is we take the safety, instead of putting it all on the various tasks, we take it out and we put it globally as a project buffer. So where the tasks were scheduled in this way, now we schedule the tasks with only 50% of the task time, because there's a 50% probability of finishing it in a shorter time. And we put all the safety at the back. So the project end time is still the same, but the last part of the project is all consisting of buffer. And we will use the buffer, some of it. And suddenly we manage the buffer instead of the tasks. And if I put it into this picture, you can see the project buffer is the project for the longest path of independent events, which is the critical path of the project. Here's the insight. In a project, the critical path is the bottleneck. And that's the key thing to manage. So we buffer it in a completely different way than in production, but you buffer the critical path with a project buffer. You put resources on standby on all tasks in the critical path. So in the chance of task A gets finished a day early, B can start the day early so that you can gain on early finishes, which in our normal project management approach we cannot do. And then everything feeding into the critical path, you put a feeding buffer. So once again, it's a bottleneck, buffer management, and protective capacity. The same concepts as in operations, but in a slightly different way. And I want to show you this slide, which combines the two, combines the operations approach and the project management approach for the following reason. In underground mining, very specifically, but quite often in open cast mining, we use the same equipment for production and development. And when there's pressure on production, the development suffers. And eventually you paint yourself into a corner. So we've developed the techniques of using both of these together. And now this black arrow shows that how do we make the choices of how to allocate equipment? Because it's the same equipment, it's the same drills, it's the same bolters, it's the same LHDs or boomers, call it whatever you want, that we used. So we need to manage both the long term and the short term at the same time. And this is not that simple. And at the same time, we want to link it to the market demand and the market promise. So in projects, the old view is to manage the task details, optimize every resource, and lowest cost by budget. In TOC, it's managing the flow of the project, bottleneck, and the buffer the project, and then we manage the buffers. So the buffers status gives us the key measurements on how to manage the system. I want to say just a few things, just one component of the way we apply TOC to supply chains. And think of underground stores in a deep level underground mine. You cannot afford not to have the right equipment underground for when you need it. Think of a mine that's at a remote site with long logistical chains. How do we actually manage the system? And we want to create a pure pull system. And I'm taking a long shortcut here. And this is how a water supply system should work. And I know today in South Africa and many parts of the world it doesn't. There's your big reservoir of water with a purification system feeding into local reservoirs. The local reservoir feeds into a pressure tower if it's a flat area, and from the pressure tower we feed the houses. None of us order the amount of water we're going to use. What you do is when you open the tap, the water is normally there. And how the system works is actually very elegant, very simple. As you draw water from the pressure tower, the level in the pressure tower will drop. And when it reaches a certain level, you trigger a pump from the reservoir, you fill it up. And as the reservoir drops to a certain level, you top it up from the purification works. This is a pure pull system. And this is what it will typically look in if I industrialize the same picture. The key insight here is the stock level here at consumer 4 is determined by two factors. It's the expected consumption during the foreseeable future and the time it requires to replenish from the warehouse. If I replenish from the warehouse once a week, I need a minimum of 1 week buffer. We normally add 50% as a safety factor. If I can get replenishment from the warehouse twice a week, or twice a week, the stock level here drops by 50%. If I can get daily replenishment, I only need to have a day or two stock only in this world. So this whole system works on the fundamental premise that you fill up the system with buffers. And as you withdraw from the lowest end of the chain, you just replenish from the previous links in the chain. It's a pure pull system. So we get rid of forecasting. You don't need forecasting. This system will look after itself. And it becomes super reliable with significantly lower stock levels than with min-max control. I mean, that was a big jump for me to make that statement. I'm not going to go into the details. This is just a picture for typical for a mining environment. If you've got a big mining organization with a central corporate hub, you've got regional hubs, and this could be different countries, and then on the mine itself. It's the same system, guaranteed availability, and it works like a dream. And it's very simple, and it really looks after itself. And the way you adjust, and then you just have to make some adjustment to the buffers. If the buffer stays in green all the time, it's too big. Make it smaller. You're wasting money. If the buffer goes into red too often, you're at risk. It's not worth it. Beef up the buffer. And so we will use the trends to determine the buffer levels. Very powerful system. So we create a pure pull system. We buffer the essential variation, replenish on actual consumption, and we adjust the buffers based on the trends. And then the second last point is, how do we apply theory of constraints in finances? There's the system. This is the mine. We've got attributable cost. This is diesel, explosives, things that we buy from the outside world to process what we want. Then we've got period cost, or in theory of constraints, we call it operating expense. Mostly period costs. And we do not allocate cost to the product. And then the financial throughput, or the margin, is the difference between the sales price and the truly attributable or truly variable cost. And that gives us the margin. And this is the true measure of income. And if this margin is more than the period cost or the operating expense, the company actually makes money. And this is what it will typically look like. Very simple, very straightforward, but with phenomenal leverage, and I'll demonstrate that just now. If the sales income is 3 million, the attributable cost is 600,000, which is fairly typical of an open cast mine, 20%. And then this is your margin or your throughput. Then we subtract the period cost, the monthly expenses, and there's the net profit. The real question is, if we've increased the production by 10%, what will happen to the bottom line? So the sales go up by 10%, the attributable costs go up by 10%. This is the new margin or the throughput. The period cost stays more or less the same, and we've got significantly more money. And we use this methodology to make very good financial decisions. And then the way we do it is, firstly, we look at how do we increase throughput in terms of quantity and quality, not cost. Cost, operating expense, or period cost, that's the last thing we look at. If you reduce inventory, you also increase the speed through the system. So reducing inventory has got a serious beneficial effect, especially in manufacturing, less so in mining, but it's very powerful. And this is the clear distinction between them. We make a clear distinction between attributable cost and period cost. And then the bottleneck determines the flow rate of the system. So if you want to allocate costs, you allocate it to the bottleneck, because the bottleneck determines the rate of the system. And that helps you to make some really good financial decisions. In order to do all of this, you need something like this. You want to shift from the world of balanced capacity or local optimized thinking to the world of flow. And we introduce what we call it a daily war room. And the war room looks at the flow, the subordination and team behavior. But the key is we need good leadership to make that transition. And this is a real challenge for many companies going forward. I'm going to skip this slide. We learned the following. It's all about shared consciousness. If you want to do this kind of shift, it's all about shared consciousness, shared understanding, creating extreme visibility, and out of that comes empowered execution. This comes from a book called Team of Teams by General Stanley McChrystal. Phenomenal read. They don't call it theory of constraints, but it's theory of constraints at its heart. I just want to say something about the long-term effects, and this you find in the Whittle consulting approach. Jeff Whittle wrote the original algorithm for pit optimization. Many of you will know the Whittle pit optimizer. It's very well known in the industry. Been around for decades. Very powerful stuff. But then they shifted that also to include the mining enterprise. And it's about max optimization of the life of mine over the whole enterprise. And it's a very sophisticated maximizer software, runs on multiple servers. It maximizes the entry fee over the life of mine. And this is typically what it will do. It will look at the mining enterprise as a whole, and it consists of the pit or underground, the different phases in the pit, the mine schedule, the cutoff grade, very, very important. The blend, whether you blend or stockpiles philosophy, your processing, product mix and logistics in the market. And here's the key insight. When you start the mine, the bottleneck will be in the mine. But you'll reach a stage where the mine can produce more ore than the processing plant can actually handle. And then the bottleneck shifts to processing. And when we get there, the processing starts getting full. Then you have to ask yourself the question, what should the processing plant be working on? High grade or low grade? And it's obviously it should work on the high grade. And then what do we do with the lower grade material? Do you throw it away or do you stockpile it? And then the whole stockpile philosophy comes in. And then you have to do this over the life of mine. And using theory of constraints and the cost approach that I've just showed you, we call it activity-based costing. These are the kinds of the results that the Whittle software or the Whittle approach will actually give you. The blue curve is the base case. And after the optimizer process is the orange curve. And you can see 37% increase in net present value by bringing cash flow forward. 29% increase in NPV, 59%, 29%. This is very powerful stuff. And this correlates to what I showed you right in the beginning. And these are the kind of enterprise input improvement results that they found. So, ladies and gentlemen, here's the big challenge. How do we switch from the world of efficiency thinking to the world of optimized flow? And I think hopefully by now these pictures will mean a lot to you, and that it will actually give you an indication of what is in store. This is the world of bottle 1. This is the world of bottle 2+. And with the right leadership, you can get to bottle 3, a world of excellence in the spirit of calmness, and the company will just pump money. And this is what it's all about. Thank you, Alistair. I think I've got a few minutes for questions.
Thanks, Arrie. Thanks so much for a really stimulating presentation there with some great results. So I've got a few questions that have come up already on the Q&A. So we've got actually 3 questions from Lebasani Mashabile. So I'll deal with all 3 of those. The first one is, what are the factors that influence the degree of flexibility in the system?
I think the original, my original approach is to really have a look at the whole system, the levels of uncertainty or the levels of variation that you have. For instance, there's no perfect ore reserve on this planet. all reserves have got huge variation in them. So you need to get an understanding of the variation that you have. You need to have some understanding about the market demand for your product. And then a very important decision, you need to decide at what level you want to invest to produce at what in other words, you're going to determine the life of the mine by your decisions in terms of financial investment and setup. And then you have to go through all these technical variations and technical factors. But then the key point here is you have to decide on your management philosophy. And the management philosophy is this real choice between theory of constraints or optimize everything or the world of efficiency. Did I answer that question good enough?
Thanks, Arrie. The second one that was posed there is, are you suggesting the bottleneck in a life of mine plan can be different resources?
Yes. Allow me to give you this example. For instance, the grindability of the different ore types. Normally, your weathered ore is at the top level of the ore body, and as you go deeper, for copper, for instance, the ore will become harder and more difficult to grind. So in the beginning, you will be able to put a lot more tons through the mill, and then probably your flotation or filters will become the real bottleneck. But as you move deeper in the ore body, the ore will become harder, and it will spend a longer time in the mill. So then your mill will become the bottleneck. And it's so important from a management strategic planning point of view that we understand this. And that has got an implication on the grade, the pit layout, on how do we plan which ores for which phases in the life of mine plan. But definitely it shifts.
Okay, then we've got two questions that are kind of similar. So I'm going to sort of combine them together. Again, one is from Lebasani, who says, creating a buffer costs money. So what do you trade off the buffer against? And from Masood Hossein, a similar question saying, would you share some good techniques to explain the working capital requirement to the management accountant who keeps pushing via management lines to reduce the working capital or the inventory?
I love this question, because if you look at the whole, if you really understand the impact of the bottleneck on the system as a whole, if your bottleneck runs 10% short because it doesn't have a feed, it's 10% of the system as a whole, not just the bottleneck. So in our experience, putting in a buffer and stabilizing the flow will pay for itself within days or weeks at the most. And so on an annual basis, it's not actually worth the conversation. That's how quickly you will recover that. And you recover it by the increased output of the system as a whole. If your system produces 10% more, you can do the calculation. You will cover the cost of the buffer within a very, very short period of time. But, and this is why I'm smiling, to have this conversation with an accountant is very difficult. So I'm not hitting at accountants, but within the accountant glasses, in the accountant binoculars, we have to shift from the cost of the parts to the cost and the output of the system as a whole. And I think that's the switch. It's not that difficult, actually. And I've had phenomenal conversations with accountants on this. And mostly they get it. And once they get it, they will become the biggest supporters of this process.
Yeah, I think that, you know, where I've seen it as well, you know, it's a sort of cost-benefit analysis that you need to do to say that, and you know, if we need to spend X amount of money to create so much improvement in PV by working on the constraint, and then you look at, you translate that into an opportunity cost.
Absolutely.
If you don't give us the money, this is what you are actually costing this operation. And it becomes a kind of compelling argument.
I couldn't have said it better.
I see we've got Wally Richards is on the panel as well. So Wally, welcome, and if you want to chip in anywhere, please do. We've got a question here from Gary Lane, and Gary gave a presentation a little while ago, also on value chain optimization.
Oh, that was very interesting.
Gary says, great presentation, Arrie. We have an experiential simulation called SciMine, and we have run it all around the world and have not yet found a team that understand or can apply any of these concepts. Why do you think we as the mining industry are not able to institutionalize this in the mining industry as part of our planning and operational philosophy?
Gary, this is a loaded question. Everybody can sense it. I think, and please forgive me for giving this example, but the bottle example helps quite a lot, because it gives you a very simple metaphor for demonstrating it. And then, I mean, today I didn't have the chance, but we developed some very simple examples of simulation. So we can do a mental simulation on the screen. We can even play dinky toys and show people what happens. But I believe the real solution is to use, and I don't know SciMine, so I'm speaking in the dark. Use simulation models, and maybe then create an experiential learning for people to do to really understand it. Would you mind if I switch back to the share screen, Alistair? I just want to.
Sure.
I skipped a slide. And that slide is actually the answer to Gary's question. Oh, sorry. Oh, there we are. This is the model that we've learned works very well. You have to create a provoking experience. And to some degree, this presentation that I gave was a bit of a provoking experience. But then with a simulation model, you can do that. To create the provoking experience, then allow for true reflection. And sometimes you need to facilitate that a little bit. And that leads to the intrinsic reframing, where people realize that their own mental models are wrong. And then they start adjusting it. But they have to come to their real insight. And once you've done that, then comes the reconstruct or the hardwiring of that new mental frame. And I can tell you from experience, that's the tough part. Because the moment things go hard or difficult, people default to their unspoken, unverbalized mental models that they hold. And that's a big challenge. So this is a constant battle. But I believe this helps you, and I think with the SciMine, you can actually do this process. I hope that answered your question.
Thanks, Arrie. So I guess you and Gary can get together later on and discuss that further. Any opportunities? George Delas, in applying theory of constraints in the plant processing space, what is the correct way of specifying nameplate capacity?
Nameplate capacity is it's, for me, normally the starting point on when you start designing, when you're in pre-feasibility or feasibility study, that's where you use nameplate capacity. And then that's all about setting up the system for a certain level of production. And we all use these numbers. But I think what you sense from what I showed you today is that we can go beyond. I wouldn't, in the design phase, twiddle with those numbers, because that puts you into a very difficult position. So we normally, when we do the capacity design for a plant, we use nameplate capacity. But then we go, but in practice, we apply these fundamental tools to then go beyond that. Now, there's one real challenge here, and that is, if we very often, when we set up a plant, we create a balanced capacity chain, where we match the capacity of the different parts of processing. And this is a big problem. So we want to suggest, use the main nameplate capacity, but then decide where you want your bottleneck to be, decide on the buffering in the process, and I know it's not that simple to do it all the time, but then set your system up so that there's resilient capacity, so it can accommodate the variation that will come. Because your ore feed is never exactly what you want. There's always variation, and you need that flexibility so that you can do it. But design it as an unbalanced system. And if I can use Eddie Goldrat's words, balance for flow, not capacity.
Okay, thanks for that one. Nali Hall says, thank you, Arrie, for the presentation. I have the feeling this one has been kind of answered already, but you mentioned yourself that this is a radical approach and the mining sector is slow to change when compared to other industries like IT. Do you have any advice to overcome resistance to change? And how do I answer the question, we've been doing this in this manner for the last 50 years, so why should we change when it still works?
I've answered partially, but I think the real challenge is to get people to see that there's a different alternative that might work better. And it's all about creating this provoking experience, showing the alternatives, maybe using other implementations, other examples to show what's actually possible. You cannot force people to change. You cannot force people to want something new. You have to invite them to do it. And we have to create that carrot. And if that carrot's big enough and the potential is big enough, then people will go for it. Eddie Goldrat used to say, and I'm sorry for quoting him again, he says, people are not resistant to change, they are resistant to being changed. So you have to create the will to change in people. And this is a people thing. It's not that simple. And sometimes you can, with the best technical results in the world, not convince people to do something different. And unfortunately, our mining industry is not that well known for adopting to new technology. When it comes to technical technology, we're not too bad. We're actually quite good of bringing in new types of equipment and so on. But when it comes to the people side, we're a little bit slow. But my experiences in the last few years, I've seen some mining companies making significant inroads. And maybe COVID is putting us in a position where we realize we have to think different. Maybe now is not a bad time to do it. Find some good examples and figure out better ways to do it.
Okay, thanks, Arrie. Just two more questions. Dalu Nube, what has been your experience in managing the challenge of poor data reliability when applying this methodology to deep-level conventional narrow reef mining?
The data that we have, you remember that graph that I showed you with all the graphs going like this, with a highly interdependent chain? our data is so contaminated with interdependent effects that the data is not worth a lot, because our data management systems are built on the assumption that everything will be fine, but it isn't. It doesn't take their interdependence into the account, because sometimes your drills, for instance, your shovel is not performing well because the fragmentation was poor. And that effect you don't see in the data. It's very difficult to translate that into the data. So what we do from a theory of constraints point of view, we try to look from the higher level aspects first, and we do not rely on data that much. We look at the data to get trends, but we do not deal with the detailed data except on the bottleneck. On the bottleneck, the data is absolutely crucial. I want to know every minute what that thing is doing. But on the resources with spare capacity, it's a bit of defeating the object of knowing exactly how they're doing, because they should be idle from time to time. And that in the data, the idleness shows up as a negative, but it's actually not. We can have a whole evening conversation just on this topic.
Yeah, we've got another webinar coming up, in fact, later in the week on metal accounting and that sort of thing. So it'll partially answer this question. And I think, you know, the issue really is that we do have technology available now, which will help us a lot with collecting data, but also understanding the variability of the data at different parts of the value chain. You know, because there's some areas where we're never going to have precision, but it's fine as long as we understand the variability.
That's the
yeah, and then Mokomotsi Molefi asks, in a plant environment, would you say culture change can be a bottleneck?
Yes, it can. And it quite often is. And very often you find that there are a few individuals, very strong personalities, maybe strong ego-driven, and they have a kind of a clamp down on the culture. That becomes a very difficult constraint to move. And I don't really have a solution for you. That's a tricky one. It's hard work, and the only way that we do it is to try to build a relationship with those individuals and to gradually help them to see differently and to start behaving differently.
Okay, thanks, Arrie. That's all the questions. I'm just checking on the chat as well. There's nothing else there. Yeah. Okay, so thanks ever so much. It was really, really interesting and exciting. We had, I think, 74 attendees, which is great.
That's great.
I've just seen another one come up here. So that's from George again. He said, thank you, Arrie, for the response in relation to plant nameplate capacity, and fully agree with you. It all comes down to where the bottleneck is positioned. Okay.
Very well.
Yeah. So thanks everybody who's been on the line.